Hello again. Yeah, so I had to go before I'd completely finished the problem because I had to go and fetch my children from school. Didn't want to be late for that, and then one thing led to another, and now it's 9:15 my time as I start this second video in the series, which is part 2 about Pascal's determinant. So if you haven't watched part 1, this may not mean too much. But let me at least do a little recap. So just a very quick one. So I'll share my screen again. So the problem was you form a matrix by writing Pascal's triangle, sort of rotating it through 45 degrees and making square matrices out of it. So here's matrix 1, 1, 1, 2 is, you see that there's a row 1 of the Pascal's triangle there. And then there's a row 1, 1, and then there's a row 1, 2, 1, but you just have to see the 2 there. And then here you see the full 1, 2, 1, and then 3, 3, which would have a 1, 3, 3, 1 if we'd only put the whole thing in, which we have done in this matrix. And here we've got 1, 4, 6, 4, 1, etc., etc. And in general, as long as you say that this is row 0, then the formula for Aij is I plus j, choose I. I observed straight away that if you just write down the formula for the problem is to show that the determinant of each of these matrices is 1. And if you write down the formula for the determinant, you really do get something that it's impossible to see why it should be 1. So I then tried doing some row operations, and I found that when I did row operations, then after a short time, I could easily get the matrix into upper triangular form with 1s down the diagonal, which, if I could prove that that always worked, would give me that the determinant was 1. Excuse me, I've got something in my throat. So here was a formula for the n by n matrix, and I then thought a little bit about what I would actually need to show was 1 here and what would to show was 0 here after doing all these operations. And I ended up realizing that one of the things I wanted to do in order to get the diagonal entries to be 1 was to prove this slightly funny looking identity here, which has a product of binomial, an alternating sum of products of pairs of binomial coefficients. And I've observed that we sometimes see that sort of thing. For example, there's a well-known identity concerning 2n choose n, but this has alternating sums in it, so it's not completely clear that you can do it by counting something in 2 different ways. After a little bit, I despaired of that, so I decided to see whether I could just write down an inverse for the matrix, which would at least show that its determinant was plus or minus 1. And then when I saw what the 3 by 3 inverse was, I thought, no, I don't like this one little bit. I couldn't see anything nice about that matrix there. So in particular, I couldn't see a pattern that I might be able to generalize. And then I wrote down once again what the identity should be, but in a slightly different form. Instead of writing 2n minus k choose n minus k, I wrote 2n minus k choose n, but that didn't seem to help much either. I also observed that it gave me a trinomial coefficient if I multiply those 2 things together after the cancellation of the n factorials. And that didn't seem to help much either, and maybe one could think of a way of making it help. And then right at the end, I just suddenly realized that if only I'd looked at columns while I was doing these row operations, I would have seen all sorts of patterns. And then after a while, and then I started to realize that I actually knew these patterns. And in fact, expressions of this kind, I have in fact seen before, but I was just not really noticing them. So at the end, I had a sort of aha moment, which I wasn't able to explain in detail, but now I can do that. So let's just, so just to remind you what the row operations were that I was going to do, I would start with a matrix. Let's say I started with this 4 by 4 matrix. The first thing I did was to take each row and subtract it from the next row, which we know will not change the determinant. So that means that this one becomes, instead of 1, 1, 1, 1, it becomes 0, 1, 2, 3. And then this third row, I'd subtract 1, 2, 3, 4 from it and get 0, 1, 3, 6. And instead of just 1, 4, 10, 20, I get 0, 1, 4, 10. So I was so focused on the rows, I didn't notice that I've got 1, 0, 0, 0, 1, 1, 1, 1, 1, 2, 3, 4, 1, 3, 6, 10. So I'm actually just getting the columns of the original matrix, but moved along. Then when I did the row operations again, something looks a bit peculiar about that. What does it? So I get 1, 0, 0, 0, 1, 1, 0, 0, and then 1, should it really be 1, 2, 2, 1? Perhaps it should. So I subtract this from, yeah, I think that's okay. So actually the columns don't look quite so nice the second time around, but that's not going to matter in the end. But when I've finished, look what I've got. I've got 1, 0, 0, 0. I've got Pascal's triangle sitting there, but in a slightly different form. 1, 0, 0, 0, 1, 1, 0. So forget the zeros. 1, 2, 1, 1, 3, 3, 1. So something interesting seems to be going on, and that would explain why I've got zeros here. So if I'd focused on the columns I got at the end, then I think I would have been home and dry. But let's focus on the columns. Let's see what happens to a column. So if I pick I might as well pick the nth column. So what does the nth column look like? Let's get a nice new page. The nth column is going to look like this: N0, N1, N2. Perhaps maybe I'll call it the kth column. K0, K1, K2. No, that's not quite right. Let's go back, be a bit more careful. It's I plus J, choose I. So if it's the kth column, then the first entry is in the 0th row. So it'll be K choose 0. The second one will be K plus 1, choose 1, I beg your pardon. So then it'll be K plus 2, choose 2. K plus 3, choose 3. I'm going to imagine I've got an infinite matrix for the moment, because why not? And I can just sort of restrict attention to some finite portion of it whenever I want to, and so on and so forth. What happens when I take the difference of this once? So I'll put a nice little arrow. It's going to go to, well, what's K plus 1 choose 1 minus K choose 0? Well, there are two ways of thinking about this. One is to say, I'm going to leave the K choose 0 here, because that's what I do. This is the first of the row operation. So the first row stays as it is, but now I subtract the first row from the second row. So what's K plus 1 choose 1 minus K choose 0? It's K plus 1 choose 0. Why? Because K plus 1 choose, K choose 0 plus K plus 1 choose 0 equals K plus 1 choose 1. That's a special case of so-called van der Monde's theorem. But I think in this context, it's a rather more fun just to say, oh, look, this is Pascal's triangle, isn't it? So we've got that this entry here plus this entry here equals this entry here. So when I subtract this entry, when I subtract this from this, I'll get this. And similarly, if I subtract 4 from 10, I'll get this 6, because the 4 plus 6 equals to 10. So it's going to sort of shift the columns along, which is exactly what we observed here. So let's go back and complete this process. What am I going to get next? To be K plus 2 choose 2 minus K plus 1 choose 1. And that'll be K plus 2 choose 1. And K plus 3 choose 2. This doesn't seem to be shifting the column along precisely. Let me just check that I've got that right. So if I want to choose k, which is one thing out of k plus one things, I can I think I should have said k choose 1 here probably, instead of k plus 1 choose 0. K choose 0 plus k choose 1 equals k plus 1 choose 1. Yep, that should have been k choose 1. And then this will be k plus 1 choose 2. So I kind of go into this knowing that something's nice, but I just, whoops, that's k plus 1 choose 2. That's nice because it continues I could replace this k choose 0 by k minus 1 choose 0. It would be just as correct. So then I have a nice pattern going on. So then it's k plus 2 choose 3, k plus 3 choose 4. Just a quick check. K choose 3 plus choose 3 plus k choose 3. K plus 3 choose 4 equals k plus 4 choose 4. So there we are. That's what happens if I do the differencing process once. Now the second time round, I'm still a little bit worried. Or am I? Okay, back to where we were here with the 4x4 matrix. So let's just take this 1, 3, 6, 10. The first time round, oh no, sorry, up here, 1, 1, 1, 1. First 1, 4, 10, 20. The first time round, I took away the 1 from the 4, the 4 from the 10, 10 from the 20, and got 1, 3, 6, 10. Second time round, I took away just the 3 from the 6 and the 6 from the 10. So the second time round, it looks as though I want to leave the k choose 0. I want to take away k choose 1 from a k plus 1 choose 2. So it looks as though I get k plus 1 choose 1. But I'm a little bit anxious that that is not. Oh no, sorry, I shouldn't be anxious here because I was thinking I needed this to end up being 1, but I don't. I want it to end up being, we'll see. So k choose 1 plus, oops, plus k choose 2 equals k plus 1 choose 2. So now I've leapt from k choose 0 to k choose 2. Let me just check whether what happens. Yeah, something's very strange. So I've got 3. Go back here once again, sorry. I've written down the formula correctly for what the coefficients are. K choose 0, k plus 1 choose 1, so that's 3 choose 0, 4 choose 1, 5 choose 2, 6 choose 3. And that goes to 3 choose 0, which I can change to 2 choose 0, 3 choose 1, 4 choose 2, 5 choose 3. And then the next time round, it's going to be 3 choose 0. And then it'll be 3 choose 1 should be. So, yes, okay, so that I'm still slightly confused, annoyingly. wait a minute, I'm replacing this. Sorry, I'm leaving the k choose 1 as it is. That's what's confusing me. So the k choose 1 stays as it is. And this k plus 1 choose 2 becomes this minus this. And what k choose 1 plus k choose 2, that's more like it, equals k plus 1 choose 2. And then k plus 1 choose 2 plus k plus 1 choose 3 equals k plus 2 choose 3. And k plus 2 choose 3 plus k plus 2 choose 4 is k plus 3 choose 4, and so on. Next round, so let me try and do it a bit more competently this time. So I leave the first 3 rows unchanged, which is nice because I've got a nice little pattern showing up. And what's the 4th row? Well, by Van der Mon's theorem, I'm going to go to k choose 3 here. And then it's going to keep going up, k plus 1 choose 4. And we can see by induction or that if we keep going enough times, we're going to end up with k choose 0, k choose 1, all the way down to k choose k. And that's actually basically finished the proof. So what that means is that if I do enough row operations on my initial matrix, I'm going to end up with 1, 0, 0, 0. And then I'm going to get 1 choose 0, 1 choose 1, 1 choose 2, 1 choose 3. And I'll get 2 choose 0, 2 choose 1, 2 choose 2. Then I'll get 3 choose 0, 3 choose 1. I can work out exactly what the matrix is that I get when I do all these row operations. And it'll go all the way up to 1, n, n choose 2, all the way up to n choose n, which is 1. Since I've got 1's all the way down the diagonal, the determinant is 1. So I did row operations that didn't change the determinant. I end up with this matrix. So determinant equals 1, tick. Let's just quickly go back to this identity that was confusing me. There was no need for it to confuse me because it's just a special case of the following fact. Supposing I start with the binomial coefficients n choose 0, n choose 1, n choose 2, n choose n. Now let's take successive differences. So the first successive difference by Van der Mon's theorem, I'll get that n choose 0 plus n minus 1 choose 1 equals n choose 1. And n choose 1 plus n minus 1 choose 2 equals n choose 2. I'm now worried that the Van der Mon's theorem seems not to be the same as it was when I was doing it up here. What is Van der Mon's theorem? It's n choose k minus 1 plus n choose k. That's the number of ways. One can do this by expanding out the formula, but that's horrible. Much nicer to say that the number of ways of choosing k things out of n plus 1. Either you insist that you choose n plus 1, in which case you get out of the remaining n, you have to choose k minus 1. Or you insist that you don't choose n plus 1, in which case you've got n things from which you can choose k. So we get this identity here. but that doesn't seem to be quite the same as saying that n choose k minus 1 plus n minus 1 choose k equals n choose k. So why should that be the case? It seems that actually it is the same. But how can it be the same? Because so here I think we've got to say we're doing, remember it's not quite the same. So if I'm choosing k things out of n, I'm either choosing k minus 1 and I'm choosing n, or I'm choosing k things out of n minus 1. But that seems like the same argument, but for a different conclusion. And I can't get this just by adding 1 to everything. So somewhere I'm making a stupid mistake. So when I chose k things from n plus 1, I can't see what I'm doing wrong. Oh yes, no, this n choose k minus 1, that doesn't look right. So what is n choose k minus n choose k minus 1? Okay, I'm going to do something really unpleasant. So n factorial divided by, just to save time now, because I'm getting myself into a slight muddle, minus n factorial over k minus 1 factorial n minus k plus 1 factorial equals n factorial over k minus 1 factorial n minus k factorial no, I don't want to do that. I want to say n factorial over k factorial n minus k plus 1 factorial times, and then this, to get n minus k factorial on the bottom instead of n minus k plus 1, I've got to add an n minus k on the top, and to get a k minus 1 factorial instead of a k factorial, I've got to get a k, so it equals n over k factorial n minus k plus 1 factorial. But I'm being completely stupid because that's not what the column was. Times an n factorial. So let's just, I apologize, but I just wrote down something wrong, which then led me into a sort of irrelevant model, which I've sorted out. But the fact I've sorted out is not very helpful because it's not actually relevant to the problem. Because the column was not n choose 0, n choose 1, and so on. It was n choose 0, n plus 1 choose 1, n plus 2 choose 2. And now Van der Mon's theorem is going to work. So n plus 3 choose 3, etc., etc. I'm writing the column as a row. So now what happens if we take differences? We get, by Van der Mon's theorem, n choose 1, n plus 1 choose 2, n plus 2 choose 3, and so on. And the second differences will then be n plus 1 choose 1, n plus 2 choose 2, n plus 3 choose 3. And then the third differences will be n plus 2 choose 1, no, n plus, again, the pattern doesn't look quite nice enough. N choose 1 plus should not be having as much difficulty with. Yes, this n choose 1, n choose 0 plus n choose 1. And that does give me n plus 1 choose 1. N choose 1 plus n plus 1 choose 1 certainly doesn't give me n plus 1 choose 2, because those two are linear and that's quadratic. So what I really meant to write was n choose 2. And then n plus 1 choose 2. I should have written n plus 1 choose 3. And n plus 2, n plus 2, this should be an n plus 2 choose 4. Just get the pattern right. I've got the right pattern now. By the way, I think this is another little kind of glimpse into the life of a research mathematician. You can see I'm making a hash of these little formulas, but I make mistakes, and after a while I see I must have made a mistake, and I go back and I'm a bit more careful about remembering what the precise formula is, and I get it right, and so what? You know, who cares if I made a little blunder along the way, as long as you hack it out in the end. Except if you're watching this, you may be getting a teeny bit lost. I apologize for that, but next step will be n choose 3, n plus 1 choose 4, and so on. We get a nice pattern coming out. Let's not worry exactly too much about what the pattern is, but it's related very much to the pattern that we had before. But the point about it is that if we now think about what these things are in a slightly different way, we see that, let me just write this as A0, A1, A2, A3, just to sort of save a little bit of notation. So that's the first row. What's the second row? The second row is A1 minus A0, A2 minus A1, A3 minus A2, A4 minus A3, so on. What's the third row? The third row is got by taking this minus this, which will be A2 minus 2A1 plus A0, A3 minus 2A2 plus A1, A4 minus 2A3 plus A2, and so on. The fourth row, I won't go much further than this, but it'll be A3 minus 3A2 plus 3A1 minus A0, A4 minus 3A3 plus 3A2 minus A1, and so on. And so we see that by just equating what we have here with the corresponding terms here, we get a whole bunch of identities that all look something like, I'm slightly anxious about actually writing anything down, but it'll be, in fact, I'm not going to write anything down, but it'll be, these coefficients here are just binomial coefficients, just 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3, they're alternating. And so I will get that some alternating sum with appropriate binomial coefficients as coefficients of these binomial coefficients will give me some binomial coefficient down there. And so I don't think I need to work out the details to convince you that it's not surprising that something like this, a sum like this, should give me something nice like 1. So presumably that's just a special case where the binomial coefficient that you end up with after doing all this equating of coefficients will be something choose 0. So that little mystery is cleared up. And in fact, that gives us a way, if we want to, well, actually, because of what we've established, that the diagonal entries are 1, this actually has inadvertently proved this identity here. But you get all sorts of identities like that. But they're special. But I've also seen it separately by, well, it's actually essentially the same argument, but by looking over here. So that looks like game over. But somehow, for me, that's not game over. And for most mathematicians, I think it would not be game over, because I've managed to verify that the determinant is 0. But I did it by doing some row operations, and it sort of happened by a miracle, although a miracle you could sort of explain, I suppose, that you do these row operations and you end up with a matrix that's also formed out of Pascal's triangle in a slightly different way. That is a proof, but somehow you can't sort of see in advance that it should be true. It doesn't sort of explain why it's true in some sense. What exactly that means is a little bit hard to pin down, but I'm left with a slightly unsatisfactory feeling that it's still a bit, it's not 100% miraculous. This is not a completely hopeless explanation. I mean, it does, I can prove everything I've said. I can prove that when I do these row operations, I do end up with Pascal's triangle like this. And as soon as I end up with Pascal's triangle like this with the zeros here, I know instantly that the determinant is 1. So in a way, that's a satisfactory explanation. But I sort of feel that there ought to be something closer to a one-line proof, or something that's sort of an observation that makes it clear that it absolutely had to be 1. And now I have to confess again that it's incredibly hard not to think about a maths problem if you know that you aren't supposed to be thinking about it. And while I was cycling to pick up my children from school, I did have one little idea, which I didn't explore at all, and it may not go anywhere. But I had the idea not here in front of you while being videoed, but sort of offline, so to speak. And that idea was another way that one might try to prove that a matrix has determinant 1 is to show that it's a power of some other matrix that has determinant 1. And it seems sort of plausible that one might be able to find some matrix, in this case, the matrix itself is 1. Maybe there's some matrix that squares to this matrix, and maybe there's some matrix that cubes to this matrix, or something like that, some nice pattern. So now let me explore that little thought, because perhaps it'll give us a really quick and nice and somehow more explanatory proof. So we can start, again, I'm going to do what I did with the first question, or with the question when I was just looking for a first proof. And this is again something that one does a lot. It's just, you just mess around with small examples and try to find some sort of nice little pattern. So I'm going to see if I can find something that squares to this. And actually, I'm just going to guess. I'm going to guess the matrix. Actually, I wanted to have determinant. Actually, it could have determinant -1, I suppose. So I'm going to guess this. I don't know quite why I'm guessing this. It just sort of has determinant 1. It's not going to be the identity or something like that. It's about the simplest matrix I can think of that does something reasonably nice. So what happens if I square that? There's also, it's symmetric, so it'll square to something symmetric, which is sort of helpful, I think. Sort of promising. So unfortunately, it hasn't worked, but it looks as though it's failed in a not too awful way. So it gives me 2, 1, 1, 1. Well, I can see straight away that if I just flip it over, then I'm going to be all right. And perhaps I should have really thought, the matrix that we're ending up with is supposed to be kind of bigger in the bottom right-hand corner. So perhaps I should have thought, actually, it made more sense to make the matrix that I guess bigger in the bottom right-hand corner. So I'll just check this again. So 0, 1, 0, 1, that gives definitely a 1. That definitely gives me a 1. That definitely gives me a 1, and that definitely gives me a 2. So that's nice. So the square root of 1 was 1. The square root of the second matrix was 0, 1, 1, 1. So it's awfully tempting to look at 0, 0, 0, 1, 1, 1, 1, 1, 1. What's the determinant of this matrix? It's going to be 1. And we seem to have a rather nice phenomenon that the determinant of the even numbered matrices will be -1, but we're going to try and raise them to an even power, at least if my guess is correct. Whereas the odd ones we're going to raise to an odd power. I can't see how to cube that straight away, so I'm just going to square it and see what happens. And I hope that we're going to see some binomial coefficients cropping up or something like that. So what do we get? I start with a 1. I should be able to do this faster. 0, 0, 1 should tell me something like that the top row. No, what does it tell me? Oh, it's the top row is going to be the bottom row of this. So 1, 1, 1. Now this is going to add the 2 bottom rows. So that'll give me 1, 2, 2. And now I'm going to add all 3 rows. So 1, 2, 3. That's quite a nice looking matrix. 1, 1, 1, 1, 2, 1. We see Pascal's triangle starting to appear. And then it's not quite right. It shows us maybe 3, 3, 6, but we haven't yet cubed it. So let's just have another little matrix. Although the fact that we've got this part of Pascal's triangle already makes me just faintly anxious. Because it's hard to see that all those terms are going to remain unaffected if I multiply by this matrix here, but never mind, let's have a go. But I think this is not going to work. So I get 1, 1, 1. Now I add the as before. Oh, no, wait a minute, I don't get 1, 1, 1. I get 1, 2, 3. E. And then the next one is going to be adding together I think I miraculously got this right, but 1, 2, let's look at columns first of all. So the first column is going to be the 3rd column here. So 1, 2, 3. The second column is going to be the sum of these 2 columns, which is, alas, 2, 4, 5. And the 3rd column is the sum of all 3. So 3, 5, 6. So that's a little bit unfortunate because we've got, instead of getting the matrix we wanted, we've got a matrix that's sort of not totally different looking, but it's not quite the same. I'm going to try something else. I'm going to forget this 1 here. So because the point there will be that somehow maybe this will be doing a bit more sort of adding 2 rows together in some way, and maybe that'll be, I don't know whether it's going to get me anywhere, but I'm just going to see what happens if I try this, which also seems to be kind of consistent with, is it consistent with 1 and then 0, 1, 1, 1? I'm not quite sure. But anyhow, it's certainly got determinant 1. So if I square that, at the moment I'm just trying to solve the problem by a massive fluke. I'm just trying to find a matrix that does the job. If that fails after a couple more attempts, then I might stop and just see if I can actually think of a matrix that would have some reason to have a power. Or actually, I still haven't run out of things I could do. I don't actually have to take a power of a matrix. I could just take some product, generalizing the idea a little bit, a product of matrices that clearly have determinant 1. So maybe that would be more promising, especially after this thing here. Maybe I should just look at what I've got here, which seems to be getting close, and see whether I can just find a matrix of determinant 1 that will just turn those 2s into 3s and that 3 into a 6. Actually, I quite like that idea, but I don't think this is going to work, but let's just have a look. I prefer the idea I've just had. So 1, 1, 0. Now I add the 2 columns, so 1, 2, 1. This is not looking awfully nice. Now I add the first 2. Yeah. Now let's multiply that one by, this is really not looking good at all, I think. So I'll multiply that. This is really not going to be nice. Multiply that by 0.01. The first row will be the first column, I mean, will be the last column. You see it's failed, but the second column will be the sum of the last two columns, 1, 3, 3. The third column will be the sum of the first two columns, which is 2, 3, 1, which is some bizarre matrix that was significantly further away from what we wanted than we had last time. So let me just go instead to the question. I had the matrix which was looking promising, 1, 1, 1, 1, 2, 2, 1, 2, 3. And I would like to multiply it by something. And that should, what I want that to give me is 1, 1, 1, 1, 2, 3, 3, 6. So what would be a natural way of getting that? I want to do it using a matrix with determinant 1. So this first column, if I want to get this first column, then I'm going to need that first column to be a suitable linear combination of these three columns, and that is not very hard. It's got to be 1, 0, 0. I want 1, 2, 3 to be a linear combination of these. This is very strange now, but let me just do it. So I have to take the third column, 0, 0, 1. So now that will give me 1, 2, 3 for this column. And 1, 3, 6. Can I express one? How do I express 1, 3, 6 as a linear combination of these? That's a bit trickier. 1 plus 2 plus 3 makes 6, but that's not super helpful. Do I really have to work out the inverse of something? Or should I just... Oh, it's going to be symmetric actually, isn't it? So won't it be 0, 1? So I seem to be taking one of these. But that can't be right. And there's... That's very strange. So this matrix, because it's the square of this matrix, should definitely have determinant 1, so it's invertible. So there must be some matrix which, when multiplied by this, gives me this, namely this to the -1 times this. And I feel as though it has to be symmetric because it's can be a product of two symmetric matrices. So what am I doing wrong? This is annoyingly puzzling. So it's funny, because I felt that my reasoning was completely watertight, but there must be some linear combination of these columns to give each of these columns, because basically these three columns are linearly independent. And in fact, we can see exactly what that linear combination is. We just, to get that 1 on 1, we just have to take one of those and 0 of those and 0 of those. So that gives me 1, 0, 0. And to get this 1, 2, 3, I have to take none of those, and 1 of those. And yet somehow to get 1, 3, 6, this matrix ought to be symmetric. So I ought to have a 1 there, but that seems to mess things up, because that would tell me that I have to make 0, 1, 4 out of these two. And that is not going to be, sorry, 0, 1, 3, no, I do mean 0, 1, 4, because I've subtracted 1, 2, 2 from it. I have to make 0, 1, 4, but I can't make 0, 1, 4 out of those two. Okay, so let's just forget, maybe I haven't actually proved this matrix has to be symmetric, so let's not assume that after all. Actually, I've just remembered that I worked out the inverse of this. What was it? 3 minus 3, 1. Let me just do the calculation. It's going to be hideous. But 3 minus 3, 1. And if I get something nasty, then I might have just to give up. Minus 3, 5, minus 2. And 1 minus 2, 1. Another thing to say here is that when I was trying to solve a problem, it's always sort of a mixture of calculation, which you try not to do as much as, but you need sort of calculation in order to get a sudden kind of conceptual insight, which then ideally shows that the calculation wasn't necessary, but you sort of can't get to that situation without doing a bit of calculation, or you sometimes can't. Okay, what's the product of this? This is going to give me the mystery matrix that I have here, and yet it's going to have to be symmetric. So I'm very puzzled. Let's just see what happens. 3 minus 3, 1. So that's 1. Am I going to get 0? Yes, I am going to get 0. And I'm going to get 0, just as I said, right? So what about the next column? So I get 3 minus 6 plus 3. So 3 minus 3 plus 6 is indeed 0. Which I knew was going to be because the matrix was symmetric, but I won't bother to calculate everything anymore. Minus 3 plus 10 minus 6, which is 1. Quick check. Minus 3 plus 10 minus 6, 1. Okay. So there's somewhere I've gone wrong somehow. But anyway, 1 minus 4 plus 3 is 0. And 3 minus 9 plus 6 is not going to be, is it? So if it's symmetric, that's going to be a 0. If this is a 1, which I suppose it's going to be, 1 minus 6 plus 6, which is 1. But that's just going to be, that's a permutation matrix. So how come it just is not the case? That's a sort of interesting fact, but what have I just done? it's not even permutation matrix, it's identity. I multiplied this by its inverse, and of course I got identity. It's embarrassing. What I haven't got is the inverse of this matrix. So the inverse of this matrix is the square of the inverse of this matrix Where's it gone? Yeah, so what is the inverse of this matrix? Do I really want to calculate this? I'm not absolutely sure. Okay, I'm going to spend a little bit longer. It's going to be slightly boring to watch. I apologize for that, but let's just see how to get the identity. So for the first column, I want 1, 0, 0 to be a combination of these. So if I take well, I'm going to have a I'll have to take the third column, I have to take a 1 there to get this 1 to work. And having done that, so I've got a 1, I want to get a 0, so I have to put a -1 there. And then having got a 1 and a -1, I'll have to have 0. Just to quickly check. So that's -1 plus 1. I guess that works. Now I want 0, 1, 0 to be a linear combination of these. And I'm going to actually, I'm going to exploit the fact that I want 0, 0, 1 to be a combination of these, and I know how to do that because it's just the first of these. And then I know the matrices are going to be symmetric. And so now what do I need to put here to get 1? -1, it doesn't matter. So I've got to put a 1 there. And that looks as though it's the inverse of this. Quickly check once more. Oh, that looks fine. So now I want to square that matrix. So 0, -1, 1, -1, 1, 0, 1, 0, 0. Squared, I'm going to write it because I'm still, even at the age of 57, find it easier to calculate products of matrices by writing them out like this. In fact, I would almost prefer to write this matrix up here, but that's going a bit far. So what is it? It's 0, 1, 2, 0, 0, -1, 0. Symmetry. And this term here is a 1, 2. And the bottom one here is -1. And then here I get a 1. And finally, the grand finale. So I'm going to multiply. So that, by the way, was working out the inverse of this matrix here, which perhaps I should have just done directly. But now I want to multiply that by this matrix here. So that's 2, -1, 0, -1, 2, -1, 0, -1, 1 times 1, 1, 1, 1, 2, 1, 3, 3, 6. Just check that really was the matrix. And what does that give me? This is supposed to be, if this is not nice, then we abandon the attempt to look for a nice proof. So 1 -1, so that's 1. 2 -2 is 0. 2 -3, that's -1. So this should be -1. Just check. What have I done? So it's 2 -3 plus 6 is -1. But here I've got 0 -1 plus 1, which is 0. So am I kind of falsely assuming that the product of two symmetric matrices is symmetric? Just nonsense. A, B transpose equals B transpose, A transpose equals sigma K AIK BKJ. Yeah, okay, I think I've been doing something a little bit silly. Equals sigma K BJK AKI. Yeah, I don't see why it should equal I've been sort of assuming for a long time that a product or two, I mean, but for powers, oh, we don't have powers here. Okay, never mind. Let me just finish this calculation. So -1 plus 4 minus 3. And then 0 minus 2 plus 3. -1 plus 6 minus 6. And finally, -3 plus 6, which is 6. So that's the magic matrix, unless I've made a mistake, that you have to multiply this by to get this. And the take-home message is this matrix is horrible. So that still doesn't prove that there isn't some matrix that gives me that when raised to a power, or some nice product of matrices that gives me the Pascal matrix, whatever you want to call it. But I haven't yet found it, except in that case of 1 by 1 matrix and 2 by and the 2 by 2 matrix. I think this is getting a bit long, so I shall I don't like doing this, but I think I'm just going to abandon the attempt because it just could go on for some arbitrary amount of time, and I really don't see why anybody should be expected to watch that happening. But I still think the idea has got something to it, that there might well be, given how nice this matrix is, some product of nice looking matrices that all each clearly have determinant 1 that gives you this matrix here, or gives you this matrix here. And if that can be done, that would just give a nice quick proof. And it ought to work just from the fact that we've got Pascal's triangle. But I think there might be some, indeed, actually thinking about it a bit further, I think there's got to be something like that, but maybe it's, I mean, there is something like that because we could just get it from all the row operations we did. So each row operation will be obtained by applying, multiplying by a matrix of determinant 1. And if we then did some column operations over here to the matrix we end up with, I can, with that 1, I can get rid of all those 1s, and this 1 I can, well, it's trivial to use column operations to make all these things 0, of course. So that would give me a whole bunch of matrices on the left and a whole bunch of matrices on the right. But that's slightly cheating. That's what I was hoping for was a much slicker example of, I mean, it was sort of a much slicker product to take. But perhaps if one took the product of all the row operations that one, I mean, all the matrices corresponding to the row operations, perhaps that would give some nice looking matrix, and one could then easily see that it had determinant 1 and multiply it by the matrix corresponding to the column operations or something like that. But I think, or multiply it by, or the inverse of it by this matrix here, which we can see has determinant 1. But I think I'm actually going to stop. And I don't think I've found, I don't think I'm sort of on the point of finding a super nice proof, but I still believe that something like that exists. So that's all I'm going to say about that problem. If anybody wants to get in touch with a much nicer proof than the one I found, I'd be delighted to hear about it. So I do plan at some point to talk a bit more about some other questions. Again, looking at them unseen. I have a source of questions that shouldn't be too hard. If the question's too hard, then I'll just have video after video of myself failing to solve a problem. That's not absolutely ideal. And there's one question I have my sights on, which was, there's somebody I know on Twitter called Mike Lawler, who drew my attention to a video of somebody else who was doing, I think what I'm doing now, is solving a problem in real time. He was videoing himself actually standing at a blackboard and had something fancy on the blackboard. And it was very nice. So that was part, I'd had the idea actually ever since doing a course and thinking, course online and thinking that actually it would be quite nice to do this. But then seeing that someone had done it, that prompted me to think I should really give it a go as well. But Mike Lawler said he would really like it if somebody tackled a particular question from the European Girls Maths Olympiad, which is apparently a beautiful question. So I've been very careful not to look at that question. I'm going to find out at some point what it is, or how to get, or just see if I think I've lost the link to it, but I'll get in touch with Mike and see if he can tell me what it is. So I may have a try of that question when I can work up the courage. But for now, I shall leave it at that point. So if you've watched up to now, I admire your stamina, and thank you very much.